So essentially what I'm going to be doing today is I'm going to be going through the quantum algorithm that I created on the Google CERT quantum computing framework. What I was able to do is I was able to create something that I'm calling a quantum activator function, where essentially this function will toggle a qubit to an activated state if at least a certain number of input qubits are set to an activated state. So let's take a look at the diagram. So in sort of section number one of this circuit, we can see that we're initializing all of our qubits, and in this case we have 10 qubits. So I'd like to say that this circuit here is a specific implementation of the quantum activator function, and it's essentially the implementation where we have 3 input qubits and we want to make sure that at least 2 of those qubits are activated. So we're going to skip by section 2 for now, but I'm going to talk about why I applied Hadamard gates there near the end of the video. So let's skip right to section 3. In section 3, essentially what I'm doing is I'm applying Toffoli gates to every single possible configuration of qubits in the 3 input qubits. So every possible way that we can choose a subset of the 3 qubits of size 2. So we apply the Toffoli gate to qubits 0 and 1, to qubits 0 and 2, and to qubits 1 and 2. And each of these Toffoli gates has a target on a different qubit, which are denoted by the 3 qubits down below. So qubit 3, qubit 4, qubit 5. So then what we're going to do is we're going to take those target qubits of the previous Toffoli gates and we're going to pass them through every possible configuration of every possible number of inputs that is less than or equal to the number of input qubits. And mathematically, we can actually prove that when we do this, when we apply, the n qubit input gates for every possible subset of qubits that we can essentially choose. So like we did with the Toffoli gates, we're choosing we're basically applying the Toffoli gates to each possible subset of size 2 of the 3 qubits, but we do that for every possible controlled gate configuration down below. We can find that this will produce an odd number of toggles. If essentially at least one of those target qubits that we saw in the previous Toffoli gates are set to the activated state. Therefore, that means that at least a pair of qubits in the input qubits is activated. So 2 qubits are activated, and the threshold function is fulfilled. So in section 4, we essentially have a 3 qubit input controlled NOT gate. And this can be actually implemented by applying a bunch of Toffoli gates and then a CNOT gate down below. In section 5, we're essentially uncomputing what we did in the previous section, which is section 4. So we're resetting those qubits that we used in the calculations back to their original state so we can essentially reuse them. In section 6, we're applying, again, Toffoli gates to every possible configuration or subset of these controlled qubits, and we're doing the same with just regular CNOT gates. So we're applying CNOT gates to qubit 3, qubit 4, qubit 5. And then all of these controlled gates have a target of the last qubit, which is qubit 9, and that's essentially the qubit that we're toggling in order to get our final answer. And when we measure the final qubit, which is qubit 9, we'll see that if the threshold function is fulfilled, then we should get an activated value for the qubit down below, qubit 9. So let's go back to section 2. The reason that I applied Hadamard gates here is because I wanted to kind of illustrate a bit of a quantum effect on this circuit. So I put the input qubits into a kind of the superposition of the different computational basis states, and I passed them through each of these. I passed them through these gates, and what I found when I measured qubit 9 repeatedly after running the circuit a great number of times, that the probability of getting the last qubit to be activated is accurate as to what we would calculate if we said, all right, there's a 50% chance that this qubit's this, a 50% chance that this qubit is this. And when I say this, I'm referring to one computational basis state or the other. And I thought that was kind of interesting because we're essentially doing this, we're essentially performing this calculation just on a basic quantum circuit, which is created from these very basic quantum gates. And I'm not really sure where this circuit could have application, possibly in the creation of quantum neural networks, maybe, because neural networks are dependent on these activator functions within their perceptron networks. Um, but I'm still unsure of the applications. Hopefully, something useful can be done with it. But I just thought it was kind of an interesting sort of way that we can apply these controlled NOT gates to create something that's very interesting on a quantum circuit. So thank you for watching, and I'm going to be posting some more content very soon.